Okay, so we talked about transformations of exponential functions. And so when we do a transformation on y equals to the x, we can show it in that form if it's solved for y. Now we're going to be a little bit, look at some applications where maybe we haven't done a vertical translation, but we've done, notice here, that would be a horizontal stretch. So t would be equivalent to x. Okay, so maybe we do some horizontal stretches, maybe some translations, but only when it considers the same base. So we're going to concentrate on exponentials of that form, and you'll notice that that form is also listed on the formula sheet. So for growth or decay, and so we'll look at the difference between the transformation form and this growth and decay, which we've already kind of talked about a little bit when we talked about doubling time, tripling time, trying to cut something in half, increasing the population by a certain percent, that kind of thing. Okay, so A, B, and P are parameters. Y is the dependent variable and T is the independent, usually time, right? It's on your formula sheet. Okay, so when would that represent a growth function? Well, remember that base of the exponent has to be greater than 1 when it's a growth. So B has to be greater than 1. Decay, it has to be less than 1, but still positive. So B would be less than 1, greater than 0. Okay? Now, when it's in this form, you always know your y-intercept. It's just the A value, because there's nothing added outside, and there's no translation in the t. So y-intercept is when t is 0. So that makes b to the 0, which is 1. A times 1 is a. Okay? And so that y-intercept is really the initial value at time 0. It's how much you have, whether it's a mass of something or the number of items or the population or the amount of money, that kind of thing. So this is sort of a basic example. It says the graph shown represents the growth of an investment A over time in years, fill in the table of values. So at time 0, we've got 1,000, and this is in dollars. We don't have to put the dollar sign if it's noted at the top of the chart. After 1 year, we've got 2,000. After 2 years, we've got 4,000. You can see what's happening. After 3 years, we have 8,000. So after each year, the amount doubles. So it's a growth as opposed to a decay, and it's actually a case where we call it doubling time is 1 year. The length of time it takes for the investment to double. So the t-intercept, actually, that should be the a-intercept. Can you fix that on yours? No, it should be we're talking about the y-intercept, that's your amount. T-intercept is here, and there isn't one. So it should be the a-intercept of the graph occurs when t equals 0. And we call that the initial investment. The amount that you actually put into the bank. In this case, that's $1,000. So in these applications, final answer, make sure you have the units, okay? Whatever it might be. So the y-intercept, or in this case, a-intercept, but in here, in our general case, is represented by the parameter a. And so in this case, we know that a equals 1,000. We don't put units into our equation. So this money is 15 units out. So we know for this, if it's a growth investment, that B has to be greater than 1. In this case, we see that it doubles every year. So that means B will equal 2. So next part says write an equation in that form y equals a times b t over p for this graph. Use the form given. So we need a. So we're using function notation. So if it says to show it in that form, then show function notation. Don't leave the bracket t out. Okay. You don't have to have function notation, but if it tells you what form, then make sure to use it. Okay, so then our initial amount, remember, is 1,000. Okay, and our B value is 2. Notice here, so that's time over P. P is the period. It means the doubling period or the halving period or how long it takes for the investment, in this case, to double. Well, if you look at your chart, it's every year. So t divided by 1 is just t, so you don't have to show anything else. You can check with your calculator. We're not going to check this one. We'll do some other work with our calculator in a little bit. You can kind of do that one in your head and check. You put 3 in. 2 cubed is 8. 1,000 times 8 is 8,000. You can check it in your chart. Okay, so here's a different situation. $1,000 invested doubles, but now every 3 years. So 1,000 to start. After 3 years, it will have double. Another 3 years, it will have double. Another 3 years, it will have double. So we're entering the same values, but our time values are different. Okay, so it says sketch the corresponding graph on the same grid and fill in the table of values to the right. So let's take a look. I need to go back to that. So this is the same. Okay, then after 3 years, it says you figured out it's going to be 2,000. It doubles after 3 years. After another 3 years, it's going to be doubled again. After another 3 years, that's going to be doubled again. So this is what our new investment looks like. All right. So what kind of transformation will get it to look like that? There? Huh?
Horizontal stretch by 3.
Horizontal stretch by 3, yeah. Okay, that's the easiest. Okay, so here describe the transformation. So horizontal stretch by a factor of 3. So that would be, I guess in this case, the A-axis.
Is it okay if we put 1 axis?
Well, for your notes it is. Just be careful on the test if it's labeled something different. Okay, so here we're just copying out. Take a look. It says if something represents the investment of 1,000 doubling every year. So remember that's 1,000 times 2 to the t. Okay, and then we do a horizontal stretch by a factor of 3. Then we remember we replace t with t over 3, or 1/3 t. Okay. Often in exponentials, when we're doing this, I show it as t over 3, doubles every 3 years. And you can check. Let's substitute 9 in. 9 divided by 3 is 3. 2 cubed is 8. Times 1,000 is 8,000. You can always check your answer when you're coming up with these equations. You're given a chart like that or a couple of values. Okay. So I just did that in my head. I didn't do it on paper. Okay. So that was doubling every 3 years. Now we're going to double every 15 years. So what happens? We start with 1,000. After 15 years, we're going to multiply it by 2. After 30 years, we're going to multiply this previous one by 2. So that's going to be 2 here squared. Then another 15 years would be 2 cubed. Another 15 years would be 2 to the 4th. You can kind of see the pattern in what you're doing. You're going to have A of t equals your initial value. We're doubling. And then we need, for example, after 60 years, we need that exponent to be 4. So 60, what do you do to 60 to get 4? You divide by 15. So that's going to be t over 15. Okay, so this t, remember, is how many years it takes to double. On your formula sheet, if you forget. All right, so what is it? What does everything represent? So y is the dependent variable, t is independent. Y represents the amount after some time t. T will have the same units as p. So that's a really important thing. The t value and the time period that it takes to double or to half or triple or wherever it is have to be in the same unit. So t is in years, t has to be in years. So sometimes we might give you 1 in months and 1 in years. You've got to make them the same. Okay? So if we say t has to be in years and we tell you 24 months, how many years is that? 2 years. We can say that takes 24 months to double. Okay? You have to know some of those. There's 12 months in a year. You don't know that? Okay, good. How many weeks in a year? 52. 52 weeks in a year. How many days in a week? 7. Okay? Does each month have the same number of days? No. Okay? Don't just say 30. It's not going to come up right. So, when we talk about investing money, what does annual mean? Yearly, exactly. What does semi-annual mean?
Every 6 months.
Half a year every 6 months, right. Monthly obviously means every month. So this is an interesting one. What does biannually mean?
Every 2 months.
Actually means it could mean every 2 years, or actually could mean the same as semi-annual. It's a weird one. I actually had to look that up because the student was doing an IA, and she talked about biannual in terms of being semi-annual, and I thought, oh, that's not right. And I looked it up, and it's a weird thing. So we always, in math class, think of biannual as every 2 years. But apparently in some situations it could be semi-monthly is every half a month. So sometimes people get paid semi-monthly, whatever the middle day of that month is and the end of the month. Sometimes people get paid bi-weekly, which in my mind is every 2 weeks. I don't know anywhere that pays you every half a week. Anyway. Okay, so the parameter A represents the y-intercept, or in particular the initial amount. Okay. All right. Again, we've talked about this before, but it's really important that you know what the p-value represents or how to get it. So let's focus here. Parameter b represents the constant of the exponential function, or in particular the multiplication factor. So for a population, if it doubles, the population doubles, then b, remember, is 2. Sometimes we might call that an increase of 100%. Okay? You keep your 100% and you increase it by 100%, so you've got double what you started with. If it triples, then b would be 3. So your initial amount plus 200% more. So 100 plus 200 is 300%, which is 3. If it halves, then b is a half. Or you could say 0.5. I would never convert like a repeating decimal and round it. So if it was dividing by 3 every time, I wouldn't put 0.33. I put 1/3 because that's exact. 0.33 would be rounded, right? In this case, that's equivalent to a decrease of 50%. And then population increases by 25%. Remember, you have to keep your 100% and add 25%. So as without a percent, that's 1 plus 0.25 or 1.25. Okay. And decreases by 25%, that's 100% minus 25%, which is 75%, or 0.75, so you're subtracting 0.25. Okay, so those are some common ones. So A is the initial amount, B tells you the multiplication factor, P is the time period it takes for B to occur. So time period it takes for that increase in population of 25%, or doubling the population, that kind of thing. The p-value is seen graphically, can be seen as the horizontal stretch factor. If something used to double every year and now it doubles every 3 years, there has to be a horizontal stretch by factor 3. That's what we did in the first example. Okay, so for a population where t is in years, then if it doubles every year, t is 1, right? Same time period. If it doubles every 3 years, then t is 3. Okay, now, if it doubles every 3 months, which we sometimes call quarterly, that's 1/4 of a year, then t is, so think about this as opposed to, it's not 3. That was 3 years, t is 3. If t is in years, we have to put t in terms of years. So every 3 months is 1/4 of a year. Same units. Okay, so if we were to put that into our equations, then we have A, B, t over 1/4, which is A, B to the 4t. Oh yeah, for this one doubles, yes. You can put 2. You don't know what A is, but you know what it is.
Well, we know A is definitely not, well, it could be 0, I guess.
No, it's not 0. It's never, A is never 0.
Yeah.
So for this particular one, because it doubles. All right, so now if we do one where t is measured in months and the population doubles every month, then t is 1. Every 5 months, then t is 5. If it doubles every year, don't put in 1 because this t is measured in months. So 1 year in months is 12. So t will be 12. You need to be careful with that. Alright, so units have to be the same. Okay, so just in summary here, A is the initial amount, which is the y-intercept of the graph. Okay. For these particular ones, there's no vertical translation, right? So the y-intercept. B is 1 plus the growth rate as a decimal, or 1 minus the decay rate as a decimal. P is the time period it takes for B to occur. You know, that's the horizontal stretch factor. And Y is the amount after some time. Then it reminds you T and P, not toilet paper, but T and P, must have the same units, and Y and A must have the same units. Okay, you do those equations there. Give you a minute or two. P is the population. Initial amount 500. T is in years. They're all slightly different. Okay, so first two are half-life type questions. Every year T stays. Every 3 years it's T over 3. Increases by 20%. So then that has to be 1 plus 0.2 every year. Increases by 20% every 5 years, so it's T over 5. Decreases by 20%, that's 1 minus 0.2 is 0.8 every 5 years. Okay. All right, a common application is investment, compound interest. So here's the value of an investment. The equation is given there. It says, complete following sentence, an initial investment of, so remember if there's nothing outside here, the initial investment will be 200, that's A value. Okay. What does it increase at a rate as? So a lot of times students will quote 1.04. Okay? They'll just look at the R. Well, you may shake your head, but I've seen it. Very smart people. Don't take the time to think about it. Okay? So it increases at a rate. So this is what you're multiplying by. Remember that's 100% plus 4%. The 100 is keeping that investment in there. The 4% is what it is increasing by. And 4% is 0.04. Okay? And then take a look here. So it's got to read what T represents. It represents months. And so here, T divided by 7, that's the time it takes for it to multiply by 1.04, that's 7. And that will be in the same units. So that's every 7 months. Okay. Next one. Initial amount is 3,000. I guess I'll put the units. I forgot to put.
It doesn't actually specify what currency.
It doesn't, but we're in Canada, so 3,000. Okay, it decreases at a rate of. Again, it's not decreasing at a rate of 83%. That's what you are keeping in your account, what you still have. So you want to go 1 minus 0.83, and that's going to be what, 0.17, okay, as a decimal, or 17%. Okay. Often there's a question on the form about something like this, coming up with those values and interpreting that kind of thing. How often? So again, this is T in years. Okay, so this 4 has to be in years. So that's every 4 years. You want to put the units in there for you. All right. Another example here. certain substance doubles its mass every 5 days. Initially, there are 80 milligrams of the substance, so 80 goes in here at time 0. Fill in the table of values and write an equation in function notation that relates the amount of the substance A to the time in days. So remember, function notation means A of t equals. All right, so it says it doubles every 5 days, and there isn't in between, so we know that you can just put the doubled value in here, so 160. Another 5 years, that's going to be 320. Another 5 years is 640. So first thing to enter in your equation is the initial amount. Then is it doubling, tripling, whatever that is? It's doubling. T for time. And in this case, it's doubling, time is in days, and it's doubling every 5 days. So that's going to be T over 5. So if it says algebraically determine, that means show your substitution. And you can use your calculator, but you show what you're doing rather than you say graphing this and finding the answer. So we're trying to find A of 12. So I don't expect you to be able to figure that out without a calculator. But by algebraically determining, you're showing the substitution. And answering to the nearest tenth. And this is milligrams. Okay, graphically determine. You have to tell, remember the steps. Y1 equals Y2 equals. We need our window. Okay, and then we're going to need to find the, in this case, when it's in our calculator, the x value at the point of intersection. Okay, so go to y equals, clear up anything that you have there. Okay, so 80, bracket 2, bracket exponent, x divided by 5. You can use the fraction form if you want. Okay, and amount to reach. So our second equation is 1,000. Y equals 1,000. It's not going to be negative, so 0 for x. Obviously, it has to be bigger than 15 days, but it's going to double, right? So it's not going to be more than 20. So you could go, if you want to show from time 0, I'll maybe go to time 20. Y0, and we've got to be up to at least 1,000, so let's go 1,100 to leave a little bit of space. I'll go up by 100. If you can't see the point of intersection in your window, then change it. 0.1, 0.100. So I want to do the x value at the point of intersection. Enter, enter, enter. Okay. Rounded to the nearest tenth, 18.2. that is in days. So we're just going to use regular rounding. 18.2, really, 18.2 won't be quite at 1,000, right? Because we're rounding down to that. But it just says regular, it just says round to the nearest 10. So. Okay, now we're going to review how to do a regression. Okay. So regression won't be on your diploma, but it will be on your IB exams. So use the graphing calculator, the table of values, to determine the exponential regression. So stat, edit, go up and clear off any lists that you might have. Okay. Then enter your two lists. So 0, 5, 10, 15. And then 80, 160, 320, 640. Not too many values, so pretty easy to enter. Okay. We already have a window set, right? Because we graphed this equation, so that's nice. So when you're doing a regression, you want to enter your equation, enter your data, then set up your window, which we already did. Okay? Then I go to y equals, I'm going to actually delete those two, even though I'm going to enter it again. I could have actually turned it off just to compare it. So I'm going to get rid of any other graphs that are in there, but I'm going to turn on my plot. Okay. Usually I keep my plot. If you want to check it, you can. Second y equals. Just check it. I always keep it at L1, L2 because that's what I always do it. That's what it's going to graph. So I'm going to turn that on. And so if I graph now, I should see those 4 points. I haven't done the regression yet, but that's just getting it set so I know that I can see it in that window. So, how do you do regression? Remember, you go to stat, but instead of going to enter your list, you've already done that, you're going to calculate something. What are you going to calculate? The regression. Take a look. This is where there's a whole bunch. Linear, quadratic, cubic, quartic, linreg switched around, ln. So there's an arrow there. You can keep going to exponential, or you could have gone up arrow. In any case, find the exponential regression, enter on it. You entered your list in L1 and L2. Most of us do. Just make sure it says that. You don't do a frequency for this, but I'm going to store it because I want to graph it. Okay? So store, you go vars for variables, y variables, function, y1. I want to put that equation that it finds into y1. You don't have that prompt like this, then you just need to, you'll see exponential regression, just do the vars, y vars, and then find your y1, and you'll be good. Calculate. Okay. And there it is. So it says round values to the nearest hundredth if necessary. So this is going to be y equals 80, 1.14 nearest hundredth, 1.15 to the x. Notice how now it's different.
This phone line can pull out like example 12 over 5, simplify raised to the
So the regression will never give you a transformation on X. It's always going to just give you X there. Okay? Are these the same? If you're not sure, let's graph that, first of all. Make sure it goes through the points reasonably well. Should go through exactly because it is, these are exact values. Okay, if I go to y equals and I put back in there my original, which was 80, bracket 2, close brackets, the exponent, x divided by 5. You'll notice the red is graphing on top of the blue, so it is exactly the same. Okay, so those represent the same function, just a different form. Okay, so there's x, so that compared to y equals 80 is 2 to the, I'll use x over 5. So it's really, we can split this up into 2 to the 1/5 raised to the x. Okay, power of a power, multiply the exponent. Well, what's 2 to the 1/5? Should be 1.148, whatever. Okay, so they're the same. This one's shown in terms of doubling time, and this one's telling you, okay, it actually leads to the next question here. So based on the regression, doubling every 5 days is the same as increasing by approximately what percent every day? Because x is the number of days. So there's your 100% for 1. So it's basically increasing by 15% every 1 day. Okay? Yeah, just so you know, in the notes, I think this answer is incorrect. I don't know what the answer is. They have like 30 or something. So just be aware of that. This is correct. But notice the difference between them. Your calculator, when you do a regression, will not ever give you doubling times like 4 with the transformation. So you can do it as kind of a way of testing, I guess, but it's not going to spit out the equation that you want in some cases. Okay. Next question. The population of a town decreases at a rate of 2.3% each year. Current population is 800. Algebraically determine the population after 5 years. So again, come up with the equation. So I'm going to use P. It doesn't say you have to use function notation, so I'm just going to use P for population. Start with 800. Decreases. So I'm going to take 100% and subtract 2.3%, and then show it as a decimal. So that's going to be what, 97.7%, which is 0.977. And then decreases each year, so that means this would be T in years. Okay, and now we want to find it after 5 years. Again, always check your units. Now, it doesn't say what to round to, but if it's a population of people, 700, it is, of town, so round to the nearest person, 712.
Oh, I mean, it doesn't actually say round, so I mean, you could convert that to like fraction and everything. And you have to take different roots and stuff. Yes.
Yeah, you're not asking. That's so then algebraically determine the number, so this is algebraically determined, not graphically determined, the number of years, so you're trying to find t when the population is 500. So now you've got 500 equals your equation, 800 times 0.977 exponent t. That's why we didn't do these at the beginning of the unit. Because to algebraically find the value, you need to know logs. Okay? So remember, you want to isolate the factor, the term, and then the factor that has the variable in it. So the term that has the variable in it is isolated, but now we want to get the factor. So divide by 800. Obviously, you can take the log of both sides, but then you'd have to use the product law and creating more work for yourself. Reduce the left side. Okay, so now you can convert that to logarithmic form, which means you would have a decimal in your base of your log, which you guys can use because most of you have that in your calculator. But there's the odd person that doesn't. In this case, I would actually just take the log of both sides that you did when you were solving last week. So then I would take the log, the common log. Okay, so then the power log brings the t in front. Okay, and then I want to get t by itself. And then in your calculator, then you don't have to use the log base. You can just go log 5 divided by 8, close the bracket, divided by log 0.977. Oh, like doubling again. Okay. So, and then it says round to the nearest tenth, which would be 20.2, which makes sense. Because this b value is less than 1, so it's a decreasing. And where it first reaches 500, if I round to the nearest tenth, I'm actually going a little bit to the right, so it will for sure have reached that 500. If I say this was 20.11, I would round down, and then it wouldn't technically have made it there. In any case, doesn't matter because it works, and this would be years. Okay. Now, if you had from here, remember as I said, you could convert directly to logarithmic form. T will equal log, with the base of 0.977 of 5/8. And remember, change of base, those are the same. So if you have that capability, which most of you do, you can just go straight from there to there. You don't have to do the common log of form. So if you did that, how would you do it in your calculator? You go math, log base, you have that capability, 0.977 for your base, 5 divided by 8 for your argument. another example, population of a species is 500 on January 1st, 2005, and it increased to 700 by January 1st, 2011. So it's a growth function. Algebraically determine the annual growth rate to the nearest hundredth of a percent. Okay, guys, see this up there? Okay, so let's see here. We want to algebraically determine. Obviously, we could probably do a regression, but we want to algebraically determine. So let's think about it. I talk about my population as P. Starting at 500, we want to figure out here, we might even show it as 1 plus R. 1 being keeping 100% and R being the amount it's increasing by, R per rate. Okay? Annual growth rate means T is going to be in years. And years since 2005. Otherwise, you would be, if you just do T as the year number, 2005, that's like big values in there, right? Okay, so now we know that it's going to be 700 after 6 years. So this is actually now not an exponential function. Remember, exponential functions have your unknowns in the exponent and unknowns in the base. And I'm just going to show this underneath because I'm writing too big. So we did some of these before. We want to get 1 plus R by itself. You could just call it B, right? It's your B value. You can call it C because it's, you know that the base of B is only B, C, whatever. I'm splitting it up so that you make sure that you give me the correct percent. But now, to get that by itself, what's the opposite of raising something to the exponent 6? 6 rooting, or I'll do it in green, or you could even easier show it to the 1/6. Okay. I mean, the 6th root, you have it in your calculator, the capability of doing that, but raising to the exponent 1/6 is a little bit easier. So now those. I'm just going to show the 1 plus R on the left now is equal to this. It's going to be plus or minus, but remember minus won't make sense. So I'm going to just cross off that minus right away. And then in your calculator, 7 divided by 5 to the exponent, 1 divided by 6. I show a few decimal places. Okay, it says to the nearest hundredth of a percent. So I'm not done yet. So again, some students will say the growth rate is 105.8%. Okay. But remember, the 1 is this. So I want to isolate. That's why I show it as 1 plus R. I want to subtract 1 from both sides. So that's the decimal form. Multiplied by 100% is 100th of a percent, so 77. Okay, so that's the growth rate. Use the 100% and add on 5.77%. Yep.
Could we just find the B value?
but and then when they want to deal with 6, and then
Oh, 6 root of that?
Yeah.
You get the same thing, right?
Yeah.
Yeah. Yeah, just like I showed you on the last one, right? This, yeah, just make sure you show your work. It's in there.
Okay.
Assuming the same growth rate predicted population for January 1st, 2023. So that would be, T is in years since 2005. So what is that? 15, 18? T is 18, so. Now, I would keep at least a few decimal places, right? I would actually try to keep all of those. So if it's still in your calculator, so in here, it's still in my calculator, I take that, raise it to the exponent 18, because I haven't even subtracted 1 from it in my calculator. Exponent 18 and then times by 500. This is for part B. And so I get 1,370. And this is I'll just leave it. Okay, so another type of question when you're trying to calculate what the half-life is, or doubling time is, if it's not given to you. So it says a radioactive substance decays from 2 kilograms to 400 grams in 15 days. First of all, notice they're not in the same unit. So you need to keep those in the same unit. I'd probably go to grams just to, so there's no decimals, but you can go the other way around, doesn't matter. Algebraically determine the half-life of the substance, so that's the time it takes for the substance to have half its mass to the nearest 100. So that's the P value. You look on your formula sheet, that's what you're looking for. You know it's half-life. So the amount is equal to, so we're starting with 2 kilograms, which is 2,000 grams. Our B value is a half, because it's a half-life question, and T over P, right? So it says, in this case, that in 15 days it goes from 2,000 to 400. So now I can put 400 in for my amount after 15 days. Okay? 15 is not the half-life. So it goes in the numerator, not the denominator. Like I was saying. Just trying to find. So again, it says algebraically, so you need to use volume. Right? Because your unknown is in the exponent. So I divide by 2,000. So that's 1/5. And again, If you want to convert it directly to logs, you can. We have a base of 1/2. Okay, or you can take the common log of both sides. And then you have to isolate t. So basically, t and log of 1/5. Sure you close the bracket on the 1/2, or you can use your fraction form. I was going to lazy sometimes to do that. It used to be that you didn't have fractions in the calculation. So. Okay, here's 106.46. And this is big. Okay. So let's think about it. After 6.46 days, 2,000 should have become 1,000. Okay. Another 6.46 days. So that's about 13 days. That 1,000 would become 500. So that kind of makes sense. Because then a little bit longer, from 13 days to 15 days, 2 more days, then you're down to 400. So logistically, does it make sense? Try to test that out in your head, right? Sometimes you'll be asked to algebraically determine that. Sometimes you might just be asked to, like, if you have a response, you can graph it, right? In this case, what you would be graphing, though, your unknown would be t. Okay, not t. Sometimes in these questions, you don't give you the initial amount. Okay? We use these percentages to compare from what you're starting with to what you end up with. So the next question says the intensity of light below the surface of a particular lake is reduced by 4% for every 2 meters below the surface. Okay, so in this case it's not time, it's distance. Complete the table shown and write the equation in function notation that relates the intensity I to the depth. So this will be I of d equals. Okay, and notice the initial amount, initial intensity, it isn't a value. It's I with a subscript 0, which means initial amount. I naught. Sometimes it's called that. Okay, so that's the number of meters below. So that's at the surface. Then 2 meters below, it's reduced by 4%. So that means 100% minus 4% is 96%, which is 0.96. And so you're multiplying that by 0.96. And then another 2 meters below that would be 0.96 squared. Another 2 meters below that, 0.96. So you can see that our initial is I subscript 0, 0.96, and then it's not every 2 meters. So our p-value is 2 there. So each time that bracket, whatever's in it, occurs, this is the independent change, the change in the independent variable. So every 2 changes in meters, we multiply by 0.96. So determine the percent of the original intensity remaining 10 meters below the surface, round to the nearest 10. So obviously you could extend your chart, but you are really taking a look at when D is 10. So I of 10 equals I naught 0.96 over 2. So we want 0.96 to the exponent 5. And it says percent, so we need to be careful on this. Actually, we'll show it to a few decimal places. I'll put the number up, 0.81537, let's say, as the initial. Okay. So this is what percent of the initial amount. This is that in decimal form. So we take that and multiply by 100%. That's 81.54 to the nearest, 81.5 to the nearest 10th of a percent. Okay, and then algebraically determine how far below the surface. So you're trying to find D, that the intensity light will be 30%, right? Yeah, 30% of the surface intensity. So now our I value here is 0.3 of the surface intensity. So I'm just substituting that in the equation. But you'll notice you don't need those I naughts, right? They divide out. So you're really looking for when 0.3 equals 0.96 to the D over 2. And again, take the log, convert it to a log. Or take the log, common log on both sides. So if you want to do, I'll do it in converting to a logarithmic form, if you want to do that. A little bit faster. But you do that log base in your calculator. Nearest tenth of a meter. So that actually, Here's 10, that goes up to 59.0 meters. Okay, so we got through most of it. Tomorrow we'll start with the compound interest, because that's a really important application. But you can certainly, there's a bunch of kind of diploma style questions to do with exponential applications, so you can work on those. That's part of your homework. Okay, so we'll start with that compound interest, and then we'll get into log applications.